Okay, so this is going to be a short recording about the potato lab and the data analysis piece, which I know that some students were a little confused about. So let me share my iPad and we'll talk about this. All right, donde. Here we go. All right, so here is the potato lab that we did in class, right? And again, we're involved cutting, well, the virtual lab did not, but it would involve cutting potatoes, weighing them before, and then putting them in various sucrose solutions, and then weighing them afterwards, all right? So we put them in 0 molar sucrose, 0.2 molar, 0.4, 0.6, 0.8, and 1 molar sucrose, right? And then you guys calculated the differences, and we saw an increase in mass here, and we saw a decrease, I can't remember, I think a positive there, if I remember, and then a decrease everywhere else. And that makes a lot of sense considering what we know about hypertonic, hypotonic, and isotonic solutions. So as a reminder, if you have a hypertonic solution, you have more solutes in that solution, and so water is going to then rush out down its concentration gradient towards the more hypertonic solution. In an isotonic solution, you have the same amount of solutes inside and outside. And so the water is in equilibrium, so it's moving in both directions equally. And then in a gotta move my face, put my face over here, all right? And in a hypotonic solution, that means that the solution has less solutes than the inside of the cell. So water is going to come down its concentration gradient, down its water potential gradient, into the cell. In this case, our mass would increase because of the water flow. Here, the mass would decrease, right? In an isotonic solution, the mass of the potato should remain unchanged, right? And that's what this whole lab is about, is to try to determine what is isotonic for a potato. What is the concentration of sucrose in a potato that would be isotonic? And what water potential does the original potato have, all right? So, and again, this table is really crucial to understand that you put some potatoes in 0 molar, 0.2 molar, 0.4, 0.6, 0.8, and 1. And then we graphed those data. So in this first graph, again, you always should look at your X and Y axes so you know what you're looking at. So here we have on the X axis, we're looking at the sucrose concentration. So again, we had a point up here at 0 concentration. We had some at 0.2, 0.4, 0.6, 0.8, and 1 molar sucrose, all right? Those are our actual data points. I made a best fit line, which is represented here by that R value. So it's closest to 100 means a perfect line, so it's a pretty close line. And then that line can be defined by this Y equals MX plus B number, all right? So what we are actually looking for here is that we are looking to see at what concentration was there 0 mass change, right? So if you look at the y-axis at the mass change, 0 is right here, right? At 0 molar sucrose, which would be this, 0 molar sucrose, you can see there was a 20% increase in mass. So here, the mass increased, right? All of these numbers down here, and that represents concentrations of 0.4, 0.6, 0.8, and 1 molar sucrose. Those were all hypertonic. So therefore, we saw a mass decrease. Water left the potato, right? We noticed that at this point too, that it's pretty darn close to 0, right? So that gives us an indication. And then we use our Y equals MX plus B, Y equals MX plus B, right? We want the Y to be 0. So we're going to plug 0 in to this equation, 0.59 5969 x plus 0.138. You solve for x. That gives you the x coordinate. And we saw, I think it was a 0.23. I think that was the correct answer. So that shows us that, again, since we're solving for x, we're looking on the x-axis. That tells us it is a 0.23 mole per liter concentration where there was completely isotonic and zero mass change. So the original potato had a sucrose concentration of 0.23 mole per liter, right? Representing where there was no mass change. So, whoops. So, therefore, no mass change at 0.23 moles per liter. And that would represent the isotonic solution, right? So we have a very similar situation when we're looking at the second graph. But again, we have different x and y coordinates. So the y-axis has not changed. We're still looking at the average percent mass change. The x-axis, however, is different. Now we're looking at water potential, right? Water potential. So those were calculated on your curve before. And what you can see is at this point up here, we're seeing an increase in mass of the potato. Any point below that 0 on the y-axis represents a decrease in mass, right? A decrease in mass. So we can do something very similar to try to extrapolate where this x-intercept would be. So again, we'd put 0 in for y, 0.0243 x plus 0.138, and we could solve for x, and x, I forget what it is, it's like negative 5 point something. Negative, yeah, 5 point, I don't know, 68, something like that, bars, right? That represents the spot where the solution was isotonic, meaning the water potential in the beaker was equal to the water potential in the cell or in the potato, all right? So at negative 5.68 bars, water potential in the potato was equal to the water potential of sucrose in the beaker. And therefore, there was no mass change and it was isotonic. All right. So let's talk about these questions. So again, we talked about how we calculated these two things using the y equals mx plus b. You put 0 in for y, and then you solve for x, right? And that will give you either sucrose concentration on the first graph or water potential on the second graph. Don't forget your units. Sucrose concentration was moles per liter, molarity. And for water potential, we're talking about bars. All right, so the second question asks, how would graph 2 differ if the experiment started with fully turgid potatoes? All right, so I'm going to come over here and clear this page. So this is graph 2. And the way I like to think about this is looking just at this, starting with this point here, right? So in an isotonic solution, our potatoes that we used had a water potential of, I think it was negative 5.68, right? What happens if we have turgid potatoes? So water potential, I'm gonna call it normal, versus water potential of the turgid potatoes. So if we had a water potential of negative sorry, I gotta move my face again. So if we normally had a water potential of negative 5.68, and now what we've done is have turgid potatoes. So what does turgid mean? Turgid means basically full of water. Turgid means that there is an increase in the pressure potential, because as water came in, the cell wall is exerting a pressure back out, right? So if you remember, water potential is equal to pressure potential plus solute potential. Solute potential, the more solutes you add, the more negative your number, right? If we have turgid potatoes, what we have done is put an increase in the pressure potential. Pressure potentials are always positive. So if we're adding more pressure potential, then what we've done is increase the water potential of that original starting potato. So what you would see is that, again, on the x-axis down here, that number, got a little bigger here, would shift to the right, right? So a turgid potato would have an increased water potential due to its increase in pressure potential. So what you'd expect is to have a curve that has been shifted over to the right. The third question here deals with, in what direction did water move before equilibrium in the full in water alone, right? So I'm just gonna draw a little beaker here. Ding, 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 ding. So in water alone is going to be hypotonic, and it's gonna have a water potential of 0, right? The potato has some solutes in it, right? And in fact, we calculated it to be about 0.23 moles per liter of sucrose in that potato. So what that means is that, again, water is going to flow into the potato. So in what direction did water move before equilibrium was reached? It moved inside. Sorry, this was shift to right. Moved inside. And why did it stop? Right? And it stopped due to the pressure potential of the cell, right? The cell wall was exerting a pressure back out. So it's just like a balloon. A balloon can only hold so much, right? So you put water in, and a balloon is eventually going to burst. However, if you put that balloon in a box and you start blowing it up, it can only blow up to a certain amount. You can't blow it up anymore, and it's not gonna pop. So that's very similar to a cell membrane in that cell wall, right? So water is gonna flow into that cell wall, into the cell membrane, but it's gonna stop at some point because the pressure of the cell wall is going to prevent it from from any more coming in. All right. So let's see if I can get to, I don't have the last question on here. Bummer. Yeah, so sorry. The last question, I'm just gonna write it over here. So the last question had to do with animal versus plant cells, right? And this had to do with the fact that which one of these could increase its mass more, right? Plants can increase the mass because they can uptake water without bursting, right? Animal cells are pretty full. They can't take in very much more water before they will physically burst open and the water will come spilling out, right? So this is what that question had to do with. So hopefully that makes sense, that plants can have a more positive mass due to their ability to uptake more water without bursting due to that cell wall. All right, hopefully that clears some confusions up, and I will post. Bye.